Okay, so next section, natural logarithm. We're going to continue with the natural log function. And the last thing we did in the last video was express the derivative of the natural log of absolute value of x, which is still just 1 over x. And then this over here is just the chain rule version of that. Right, so we're going to do this. The next very important property here, this is theorem 5.5. And it's really just saying the opposite of this. If you know the derivative of log of absolute value of x is 1 over x, then we can take the integral of 1 over x. And that should be natural log of the absolute value of x plus c, right? Indefinite integral. So this might not seem like anything much to you, except remember what this is. 1 over x is also x to the negative 1. So there's another way to write it. And in fact, this completes the power rule. If you remember, the power rule for integrals, x to the n, this was equal to x to the n plus 1 divided by n plus 1 plus c, as long as n was not negative 1. Okay, so this is the power rule for integrals. However, we had this one exception. And so here's the exception. When n is negative 1, you don't plug it into the power rule here. You'd be dividing by 0. You don't want to do that. Instead, the integral of x to the negative 1 is natural log of absolute value of x, don't forget the absolute value, plus c, because it's an indefinite integral, of course, right? So that completes the power rule, right? Now we can take the integral of x to any power, including negative 1, right? Because up till now, you should not have seen the integral of x to the negative 1, or 1 over x. That did not come up yet, for the very reason that we didn't have the natural log function yet, but now we do, right? So that's the idea. And maybe we should write, instead of this version, we should write the substitution version, which goes like this. If you have the integral of 1 over u du, that's just natural log of absolute value of u plus c. And you might think, well, isn't that the same thing? Just change x to u. Sure, same thing. But in this case, we're using u in case we need a substitution. Okay, so we'll see that when we do some examples. Let's do some examples down here. Okay, so we have the integral of x over x squared minus 25 with respect to x. Again, it's a quotient, and you should know by now there's no quotient rule. So the only technique we know of is substitution. So what should our u be? Well, it could either be x, the numerator, or it could be the denominator. I guess it could be x squared, but that's sort of unusual. You could do that. If you're doing u equals x, you realize that doesn't help at all. All you're doing is changing all the x's to u's, but it's essentially the same problem. Right? This is not any easier than this. In fact, it's the same question. It's this, everything's the same. Whether you call it x or u doesn't matter, right? So yes, if you find yourself doing u equals x, you're probably not doing anything, right? You're not changing the problem in any substantial way here. Okay, so we're not going to use u equals x. So if it's not the numerator, maybe it should be the denominator. So I think that's what we're going to do. U is going to be the denominator, x squared minus 25. Okay. Again, the only other option that I can see here is to let u just be x squared by itself. But you'll see that doesn't work exactly in one step anyway. It might work eventually, but it's probably better just to let u be the entire denominator here. So what's my du? My derivative is just 2x minus 0 with respect to x. And maybe we should rewrite this So let's think of this as 1 over x squared minus 25 times x dx. Right? So that's in the numerator, if you like. So you can see that I have my x dx here, right? But what am I missing? I'm missing the 2 in front, right? To change this to du, if I want this to be the same as du here, and this would become 1 over u, then I have to insert a 2 here, right, to make it match with this. So if I multiply by 2, I also divide by 2 on the outside. And if I do that, everything should work out perfectly. I have 1/2 the integral of 1 over u times du, which is just another way to write 1/2 times the integral of du divided by u. Same thing. Okay, well, right. Or if you prefer, you can write 1/2 the integral of u to the negative 1. But you're not using the power rule, you're using this rule here. Or actually, you're using this rule here because it's a u instead of an x. But there it is. It's the natural log of the absolute value of u. So let's go way over here. I'm just going to copy this down again. Right. So this integral is just going to be, don't forget the 1/2 in front, natural log of absolute value of u. Well, I was going to do everything at once here, but this is a u. Don't forget the plus c because we took the integral. And now let's just change u back to x squared minus 25. And there we go. Right. That's the original integral here. And again, if you don't believe me, take the derivative and check. Right? When you take the derivative, you're going to use the chain rule. The chain rule is, right, the derivative of this is 2x, and you cancel the 2's, but you still have the x on top here. And then when you take the derivative of the log, right, the x squared minus 25 goes into the denominator. So I'll let you do that. Take the derivative of this, make sure you get this integrand here, right? Okay, so that's substitution and using the integral of 1 over x or 1 over u. Well, okay, maybe we should do one more. Okay, so this will be a definite integral to mix it up a little bit. And we're going to integrate x squared minus 4x minus 10 all over x plus 2. Okay, so again, quotient, right? But there's no quotient rule, so don't even try it. Just doesn't work. So this looks interesting here. Because you're tempted to say, well, u might be what's in the numerator, x squared minus 4x minus 10. And then the derivative of that would be 2x minus 4 dx. But there's a couple of problems with that. First of all, even if you factor out the 2 here, you don't get x plus 2, you get x minus 2. Right? You want to get x plus 2. But even that's not going to help because it's in the denominator. You need it in the numerator with the dx. So that was bound to fail, right? That just wasn't going to work here. But again, when you're doing substitution, it never hurts to guess. But when your guess is wrong, you look for another u. So what else can u be? Well, it could be just the x squared, but that's not going to match with all of this. How about just the denominator? Right? Because that was exactly what we did in the previous problem. We let u be the denominator here, right? Right. So, yep, we can try that. But then when we take the derivative of u, we just get 1 plus 0. Right? We just get 1 times dx, or we get that du is the same as dx. And you can see that's going to be a problem here because in the numerator, we still have all these x's. So I changed the x plus 2 to u, and I changed the dx, right, to du. But now we have all this other stuff that we don't really want, right? the x squared minus 4x minus 10 doesn't go away. It's still there, and you can't mix your x's and u's, right? So what to do? Well, here's the trick, right? And we've seen it once before. When you have x's still, you can rewrite them in terms of u, right? Just take away the 2 from both sides. X is the same as u minus 2. So all we have to do, everywhere we see an x here, replace that x here and here, right? Both these x's with u minus 2. Okay, I'm running out of space, so let's do that down here. So this will be u minus 2 squared minus 4 times u minus 2 minus 10 all over u, and then times du, because that was the same as dx, right? They were the same. And now we get this. And now you might think, wait, this can't be any easier than what was up here, right? Because it's still a fraction, and there's no quotient rule. True, right? But we changed everything to u. Let's see what happens if we multiply out the numerator now, right? So again, a lot of algebra here, but let's multiply this out and see what we get. We should get, again, everything all over u. We still get du, but this becomes u squared minus 4u plus 4, right? When you FOIL that out. Then we get minus 4 times u, right? And then negative 4 times negative 2 is positive 8 minus 10. Okay, so just combining like terms, we only have 1u squared on top here. We have, let's see, negative 4u plus another negative 4u, that's negative 8u. And then we have, what else? We have 4 plus 8 is 12. 12 minus 10 is 2. So plus 2. Make that plus a little bigger, plus 2, right? du. Okay, how does that help? Well, notice that the denominator is just a monomial. It's just u. It's just a single term. So we can split this up, right? This was a technique we learned way back in chapter 4, right? In 4.1, I think. We just get u squared over u minus 8u over u plus 2 over u du. And u squared over u is just u. Here the u's cancel, so you just get minus 8. And then this is 2 over u, which you can leave it as 2 divided by u, or 2 times u to the negative 1. Right. And now just use the sum and difference rule, right? When you integrate u, I'm not going to, oh, you know what? I'll write it out one last time. The integral of u du, right, minus the integral of 8 du, plus 2 times the integral of u to the negative 1 du, right? That's just the sum and difference rule, and the constant times function rule. So now when you integrate, you get 1/2 u squared minus 8u plus 2 times, well, this is the exception to the power rule, right? You get natural log absolute value of u. And then because it's indefinite, don't forget your plus c. Hang on. I forgot this was definite. This is 1 to 3, right? Oops. So, yep, we don't need a plus c. We have to plug in, not the 1 and the 3 here. Not the 1 and the 3, because that's, what is that? That's x, right? This is x equals 1 and x equals 3. When you switch to u's, what are the values of u going to be? Well, u is just x plus 2. So 1 plus 2 is 3, and 3 plus 2 is 5. So we could have done that all along here, right? This goes from, 3 to 5 instead of 1 to 3. Right? Yep, 3 to 5. Or, okay. So we're evaluating this between u equals 3 and u equals 5. Okay. So that's not hard to plug in here. Let's plug in the 5 first. 5 squared is 25. Well, okay, so 25 over 2. We can do that in our heads, right? Minus 8 times 5 is 40, plus 2 times the natural log of 5. Now, why don't I need absolute value here? Because 5 is positive. So you can put absolute value if you want, but it's redundant. It's not necessary here, right? Now, what do you get when you plug in 3? You get 9 over 2. Minus 8 times 3 is 24. Plus 2 log of 3. Again, we don't need absolute value because it's positive, right? Oh, and I should have just enough space to write the answer here. So 25 minus 9 is 16. 16 divided by 2 is 8. And then we have negative 40 plus 24, which is 16. And then we have, well, 2 log 5 is actually the log of 25. 5 squared is 25. Plus, oh, actually minus 2 log 3 is log 9. So this is going to be 8 plus 16 is 24, plus the natural log of 25 minus the natural log of 9, or better yet, the log of 25 divided by 9. And I think that's it. Hang on. I know I was going to mess up somewhere. So we have negative 40 plus 24, right? Minus a negative 24. So that's minus 16, not plus 16. Oops. Yep. So 8 minus 16 is not 24, but negative 8. There we go. All fixed. So yeah, negative 8. 8 minus 16 is negative 8. So this is the most concise way to write it. Obviously, this is, you know, if you plug this in your calculator, you get a decimal approximation. I'm not sure I feel like that, but all right, let's do it. All right, so plugging it in the calculator, this comes out to be about negative 6.9783. Well, it's 4 decimal places. So yeah, about negative 6.98. It's practically negative 7, but right. So that's the approximate, and then right here's the exact. All right. Well, that's how this goes for definite integrals. Again, you should just get a number, so don't forget. I almost forgot, when having done all this, this looked like a indefinite integral. I just forgot the 2 limits of integration, the 3 and the 5. Right. Obviously, if you, at this point here, if you go back to x, if you replace u with x plus 2, then you can just plug in the 1 and the 3 again, but you get the same answer either way. Okay, so next example, we want to evaluate the integral of tangent. Right. Now this is one that you may have been very curious about, because we know the integral of sine, right, is just negative cosine plus c, and the integral of cosine is sine. But that was it. That was basically all we did. Oh, of course we did the combination ones, right? We did, for example, the integral of secant squared was tangent. So don't get confused by that here. We're not doing the integral of secant squared. We're doing the integral of tangent, right? Which is not secant squared. Right? If you take the derivative of tangent, you get secant squared, right? So that's the opposite of this. I shouldn't say opposite, that's the inverse of this, right? So these two things here are saying the same thing, just in reverse, right? One is a derivative, one is an integral. Okay. So yeah, up until now, we weren't able to do the integral of tangents, right? So how can we integrate tangents? Well, so one thing you might try, of course, is just the definition of tangents. Tangent is really just sine over cosine. Huh. Well, again, it's a fraction, so we're taking the integral of a quotient, but because there's no quotient rule, we're left with substitution. So we can either let u be sine, but remember, the derivative of this will be cosine, but the cosine's in the wrong place. It's in the denominator, right? Remember, we want du to be cosine of x times dx. We do not want du to be dx divided by cosine of x, right? Because that would actually be secant x dx. But we don't, we don't have a secant here, right? So that's not going to work. We have a cosine, right? So, yep, so that didn't work. So then you try the next obvious thing. U would be the denominator, cosine of x. And then the derivative of that would be negative sine of x dx. So let me just copy that down here. This is the integral of sine x times 1 over cosine x dx, right? Well, okay, I wrote them in the wrong place. So let's do the 1 over cosine first times sine of x dx. That looks a little better. Now you notice we're not quite complete here because there's a negative in front of the sign, whereas there's no negative in front of this sign. That's a dot, not a negative. The dot for multiplying. Oh, maybe I can just get rid of that. So, okay, so we're missing a negative sign, so that's just a negative 1. We can multiply by negative 1, and we can divide by negative 1 on the outside. But divide by negative 1 is the same as multiply by negative 1, right? So this is our du now. That's our du. And what we get is negative in front, right? And then 1 over cosine. So this is du over cosine of x, which was u. So this is du over u. And, well, if you don't remember that, look it up. Here it is, right? It's the integral of 1 over u du is the natural log of u in absolute value. So this is going to be, don't forget the negative sign in front, natural log of absolute value. Put the u first. This is indefinite, so we do need a plus c here. But what was u? U was, well, way up here, cosine of x. I was going to do it all at once, but do it in 2 stages. So there we go. There's the integral of tangent x. Right? It's negative natural log of absolute value of cosine of x plus c. So if you don't want to go through this all over again, you should probably memorize it. You should probably know this. It'll come in extremely handy, especially when you take calculus 2. That this comes up, I would say, often enough where you probably should just know it. But if you forget it, look, you can do this, right? You can do the substitution. U is the denominator, u is cosine, right? And then when you do the substitution, you gotta, you get this 1 over u du. And then don't forget that that's the natural log of absolute value. Right? And do we need absolute value here? Well, remember, cosine varies between negative 1 and 1. That's the range of the cosine. So, sure, we could be taking the absolute value of, say, negative 1/2. Or sorry, the natural log of negative 1/2, which would be undefined. So we do need the absolute value in this case, because cosine, cosine it could be negative or positive. So because it could be negative, the absolute value is not optional here. It's necessary. Okay. All right. Well, let's do another one. Obviously, the integral of cotangent is not going to be that much more difficult here. So the integral of cotangent x dx. Oh, let's do it. We'll do it quickly. It'll just take another minute. So cotangent is cosine over sine. And by now, you realize that u should be the denominator, not the numerator. So, yep, so u is going to be sine instead of cosine. And then the derivative of sine is cosine of x dx. And so all of this in the numerator here, that's our du. Right? So this is just the integral of du divided by u, which is, again, natural log of absolute value of u plus c, or in this case, the natural log of the absolute value of sine of x plus c. Okay. So again, the integral of cotangent is natural log of absolute value of sine. All right. Now we should do the integral of secant. So we want to evaluate the integral of secant of x dx. Well, the only thing I know to do here is to change secant to maybe 1 over cosine dx, right? Well, okay, then I don't think we have a choice here. U has to be the denominator, cosine of x. The problem is that the du should be, negative sine x dx. And we don't have that in the numerator here, right? We have the negative 1, but if you remember, we can't multiply by sine x and divide by sine x. Why? Because x is not a constant. So that's just not going to work here, right? So we're kind of stuck at this point because we tried the only substitution that we could possibly do here, and it just doesn't work because we're missing a sine x, and we can't just replace it with that. So we have to be, I would say, a lot more clever about this. I'm not going to change the secant into 1 over cosine. I'm going to leave it as 1 over as secant over 1. I'm going to put the dx way over here. So here's the trick, right? The trick is to multiply by 1. Just some form of 1. Like I say, you have to be very clever. So what am I going to multiply numerator and denominator by? So let's try this. Secant of x plus tangent of x. Right? Really? So where does that come from, right? How is that possibly gonna help here? So let's multiply out. In the numerator, we get secant squared times secant squared plus secant times tangent. And I think I'm gonna I'll leave it like that, right? So secant squared of x plus secant of x times tangent of x, all divided by, well, this is 1 times secant plus tangent. I'm going to switch these. I'm going to write this as tangent plus, tangent of x plus secant of x. So do you see why I switched them? Because now I'm hoping it's more or less obvious. Look at the denominator carefully. We have tangent, right? What's the derivative of tangent? Secant squared. We also have plus secant. What's the derivative of secant? Secant times tangent. So see how well that worked out almost too perfectly here, right? So my u is still the denominator, secant plus tangent, or in this case, tangent plus secant. I think in the end, I should have switched these instead. We're going to switch the order here at the end. But for now, tangent plus secant is fine because the derivative of that is secant squared x plus secant of x times tangent of x. And all of that times dx. So we need parentheses around this, and the dx is in the numerator, of course. So that little trick worked perfectly because the numerator is just du and the denominator is u. And the integral of 1 over u is natural log of absolute value of u plus c, which in this case u is tangent plus secant. Or, if you don't mind, I'm going to switch the order one last time. I'm going to write it as secant plus tangent. I'm not exactly sure why, mostly because that's how it is in the book. So there's our answer, right? The integral of secant of x dx is the natural log of the absolute value of secant of x plus tangent of x plus c. Again, this is one you probably should try to memorize, only because look at how complicated this was. Right? Are you seriously going to think, oh yeah, just multiply by secant plus tangent over secant plus tangent? So I don't know who came up with this crazy thing here, this factor here. But it works, right? It ended up working. But it's not one that, you could spend hours and hours coming up with something that works here. Cosine plus negative, cosine minus cotangent, or, cosecant plus sine squared or something. You can try that over and over, and the only thing that seems to work here is this tangent plus secant or secant plus tangent. And that's how this goes. Yeah. So obviously this was a lot harder because the obvious thing to do here doesn't work, right? We tried this, doesn't work. We had to be a lot more clever, come up with this really, almost impossible trick here. Who would ever think of this? So yeah, and I have no idea who came up with this. I'm guessing either Leibniz or Newton or maybe both, but not sure. Maybe it wasn't until Euler figured this out. He did a lot of this. But whoever figured that out, my hat's off to them because they were super clever to get this. So before we go on, we should note the integral, just to finish this off, of cosecant of x. So you do a very similar trick, and it turns out to be negative natural log of cosecant plus cotangent. So maybe not a surprise at this point, but again, one that's definitely not obvious. So that does it, right? Now you know the integral of sine, cosine, way up here, right? You know the integral of tangent, which is here. You know the integral of cotangent, which is this thing here. And you know the integral of secant, and you know the integral of cosecant, which are over here. So again, you should know all six. The 6 trig functions, it's very handy to know, especially if you're going on to Calculus 2, because these are going to come up over and over again. Okay, so I guess we should do maybe another example. Oh, I'm going to run out of space, so I'm going to clear this, and then we can start over. All right. Great. So, all right. So our first example will be as follows. Okay. Integral. We'll make this an indefinite integral again. The square root of x over the square root of x minus 4. Yep. Not clear what to do here, but there's really only 2 choices. Either the numerator, right, will be our u, or the denominator will be our u, right? And up until now, it's pretty much been the denominator consistently, right? That would be our u. And I don't think this is going to be any exception here, right? We will see examples where u is actually the numerator, but that's pretty rare, right? That's pretty rare. So we're going to let u be the square root of x minus 4, whatever's in the denominator, right? So what's du going to be? Well, du is going to be the derivative of this, which is 1 over 2 square root of x. Okay, so the 2 is not the issue here, right? We can put a 2 multiplied by 2 on the outside. So the 2 is not the problem. The problem is the square root of x is in the denominator, not the numerator. It's in the wrong place. Okay, so it doesn't look like this is going to work. Right? It doesn't look like this is going to work here. Except it has to, right? The only other choice is u is just the square root of x, and I think that could work too. But this way I think works a little bit more directly. So here's what you have to do. Add the 4 to both sides. The square root of x is really u plus 4. And let's bring that to the numerator here, right? And the dx, so we did this right. I shouldn't have crossed it out, right? So du is 1 over 2 square root of x times dx. But what we should have done is multiplied both sides by 2 square root of x. Equal, well, I'll put it on the left here. So dx, the dx should be 2 square root of x du. Right? But remember, you can't mix your x's and u's, but what's the square root of x? It's up here, right? It's just u plus 4. So bring that down here. This is going to be 2 times u plus 4 du. Okay, so now I think we have everything we need here, right? Dx is just, well, yep, 2 times u plus 4 du. And x is, well, we never needed x. The square root of x is u plus 4. So putting this all together, and maybe I should copy this down here. Here was the original problem. Now, do the substitutions, right? The numerator, the square root of x, is just u plus 4. The denominator, this is just u. And the dx is this thing up here. It's a 2, which I can bring in front, times u plus 4 du, right? Yeah, the 2 was originally here, but I can bring that in front because it's a constant. Okay, is that all right? And then notice what the numerator is. It's u plus 4 times u plus 4. So it's u plus 4 squared over u du. And now we're off and running. I think the only option here at this point is to multiply out the numerator. And then split it up, right? This is going to be u squared over u, which is u, plus 8u over u is 8, plus 16 over u is 16 times u to the negative 1. And now just using the sum rule. Oh, I'm sorry. All right, so using the sum rule, this is just going to be the integral of u is 1/2 u squared. The integral of 8 is 8 times u. And the integral of 16 over u, maybe I should have left it like this, right? It's just 16 times natural log of absolute value of u. Right. Indefinite integral, so plus c. And now just distribute the 2 here. So 2 times 1/2 is 1. We get u squared plus 2 times 8u is 16u. And then 2 times 16 is 32 times natural log of absolute value of u plus c. And there we go, right? So that's the answer to this problem, except, hang on, this was x. So we have to write this in terms of what x is. And notice we never did figure out what x is. X is going to be u plus 4, the whole thing squared. Oh, I'm off screen again. All right, so I'll write it down up here. Right, so u was x plus 4 squared. Is that right? Oh, no, no, u was the square root of x minus 4. Big never mind there. I got it backwards. Yep, x is u plus 4 squared, but u, way up here, u is the square root of x minus 4. Sorry about that. Square root of x, and then minus 4. So plug that in all down here. And so square root of x minus 4 squared plus 16 times the square root of x minus 4 plus 32 times the natural log of absolute value of square root of x minus 4. And yep, that could be negative, so we do need absolute value. Obviously, we should probably multiply all this out. You're going to get x, the square root of x squared is x, and then minus 8 times the square root of x plus 16 times the square root of x minus 64 plus, and then there's no way we can split this up, so this we have to leave that alone. 32 natural log absolute value square root of x minus 4. Right. And we can clean this up a little bit more. We have negative 8 square root of x plus 16 square root of x. That's positive 8 square root of x. So I think x is the only x term. So plus 8 square root of x. And then 16 minus 64. 16 minus 60, hang on, 64, negative 48. And then plus, 32 times the natural log of absolute value of square root of x minus 4. Finally, plus c. And there we go. All right, so that was a long one. Right? This was not an easy one by any stretch. But it still involves substitution, right? And it involves the little bit of a clever trick here of solving for the square root of x and then rewriting the square root of x as u plus 4. And you get another u plus 4 with the dx here becoming 2 times u plus 4. So not an easy problem, but doable as long as you're comfortable with substitution. And finally, we did need the log one here, right? So right, except for this term here, this would have been one that you could have done way back in chapter 4. But yeah, the 16 over u, the integral of that is, 16 natural log of absolute value u, which you did not know that in chapter 4. Right? One more thing, if you look in the back of the book will have this answer. It's going to be x plus 8 square root of x plus 32 times the natural log of absolute value of square root of x minus 4 plus c. Right? So that's the book's answer. And you might think, oh, wait a minute, I got it wrong because I have this negative 48 here. That's not in the answer. So what did I do wrong here with this negative 48? Well, where did the negative 48 come from? It came from the 16 minus the 64, right? So that's definitely negative 48. I checked on the calculator. I think that's right. So you might think, well, then I must have done something. Maybe I multiplied wrong. I don't know. And the short of it is, you didn't do anything wrong, right? So your answer is perfectly acceptable, right? It's perfectly correct. Nothing wrong with that. And the book's answer is also correct too. Nothing wrong with the book's answer. Huh. Well, you might think that's impossible. How can they both be right when, negative 48 does not equal 0, right? So they can't both be right. Okay, trust me, they're both right. And here's the trick. See what I did there? It's very subtle, but right over here, I marked this instead of C as C1, and I marked this as C2. Right? They don't have to be the same C's. They're different C's here, but they're both constants, right? So it doesn't matter what you call them, whether you call it C or D or E or K or W, right? I mean, we usually use C for a constant, right? So there it is, right? The C2 here is really just C1 minus 48. So that's why they're both correct, right? Right? So the way I did this, my C, I didn't incorporate this negative 48, but the negative 48 is a constant. So there's no reason to have the negative 48 there. You can absorb that into the C. The C absorbs any numbers like negative 48, right? So yeah, I mean, you don't have to do that. If you want to leave the negative 48, that's fine. There's nothing wrong with it. Except it's just not necessary, right? Because the negative 48, once again, is a constant, and that constant can be absorbed into the C here, right? So if you want to do that, great. If not, just leave it as it is. Just recognize that your answer is correct, the book's answer is correct. Just because the book doesn't have the negative 48 doesn't mean it's wrong. It just means that, well, they absorbed that into the C, and they just called it, say, C2. So yeah, that was a hard problem. And I feel like we can do one more, although I might run out of space. So let me clear this one more time, and yep, and just move up. So let me see. Can we do one more? Yeah, we'll do one more. I'm just trying to decide which one to do. All right. All right, let's do a definite, or let's do an area problem. Okay, find the area under the under the graph of the function x over x plus 3 between x equals 1 and x equals 5. Okay, well, hopefully you remember that to find the area, you take the definite integral from x equals 1 to x equals 5, and now you just integrate the function, x over x plus 3 dx. Okay, so what's the idea here? Well, again, when you see a quotient, you know there's no quotient rule, so you can either let u be x, which doesn't do anything, or you can let u be the entire denominator, x plus 3. And if you do that, don't forget that x is really u minus 3, and dx is the same as just du minus 0, right? So when you transform this, this becomes x, which is u minus 3, divided by x plus 3, which is u, and then dx is the same as du. Now, what are the limits here? Instead of x equals 1 to x equals 5, u is going to be 1 plus 3, which is 4, and then 5 plus 3 is 8. Okay, so again, you don't have to do that. You can leave them as 1 and 5 as long as you go back to x in the end. But I prefer to do it this way. Right? So how do we integrate this? Well, split it up, right? We get u over u minus 3 over u, which of course is just the integral of 1 minus 3 over u. And then you can integrate each one separately. Oh, actually, let's just do the, I think we can figure out the antiderivative of this, right? The integral of 1 is just u, and the integral of 3 over u, 3 is a constant. It's going to be 3 times the natural log of absolute value of u plus c, except this is definite integral. So all we need to do now is plug in the 4 and the 8. And, well, let's do the 8 first. So u is 8 minus 3 times natural log of absolute value of 8 is just 8. We don't need absolute value here. And then plug in the 4. So 4 minus 3 log 4. So we get 8 minus 4 is 4. And then we get, let's see here. This is going to be minus natural log of 8 to the 3 plus natural log of 4 to the 3, right? It's minus a negative, so it's positive. And then I brought the 3 into the exponent. So the 4 is on the outside, and then we should do plus natural log of, right, this is natural log of A minus natural log of B is the natural log of A divided by B. And I think we're almost done. We could do 4 over 8 is just 1 over 2, and then to the third power, right? So this is 1 over 2 to the third power, which is the natural log of 1/8, or if you prefer, 4 minus the natural log of 8. Or even better yet, 4 minus 3 log 2. Right, and I'm basically not too picky about this. You can leave it any way you want here. Although, don't leave it like this. It's just a little bit messy. Yeah, but you should convince yourself that all of these are equivalent. These are just the properties of logarithms. So that's it. Again, you can get the approximate answer, but let's say the question was to find the exact area. In fact, that's probably what it's going to say. Find the exact area, which means you're not going to approximate this. You want one of these exact forms here. Yeah, and some of you may know a way to do definite integrals on your calculator. If not, again, a good way to check is to do secant and then math. I want to say it's number 7. It's the one that has this with it, which looks like an indefinite integral, but your calculator's not going to do indefinite integrals. This is for definite integrals. So I don't remember if it's 7 or 8. I don't have my calculator handy. Yeah, you do the secant and then the math, and then I don't know if it's 7. Could be 6 or 7 or 8. But it's the symbol where you see this, and then that just means, right? So, right, we're presuming that you already graphed the function, so you're going to graph, the function in this case is just x over x plus 3. And your lower limit here is going to be, well, okay, go back to the original one. Your lower limit will be 1, and your upper limit will be 5. And then your calculator will spit out the decimal approximation. So I know, you can do that to check this answer, but I want you to get used to this technique. So I want you to work it out by hand. So it's going to say that on the test. Find the exact area, and of course you must use the techniques we talked about right, in class, or at least in the video here. All right, so I think that's 5.2, or whatever section this was, 5.2. All right, I hope that helps.